In this video, I want to discuss rolling without slipping on a flat surface. Now, this is not what we call fundamental physics. It's not Newton's laws or the conservation laws or anything like that. However, it plays such a crucial role to such a large number of problems that we want to solve or are assigned when we study rotational motion, that if you don't have this concept down, many problems that we want to solve may very well be impossible. So let's take a close look at rolling without slipping and see what that means. Okay, so I am going to assume throughout here that I have a flat surface. And now I have a round object. Could be a cylinder or a ball, and it's going to be rolling without slipping on this surface. Okay. So now if it's rolling without slipping, that means this object is rotating. So let me pull it away from the ground for a moment. If we sort of go into the reference frame of the center of mass of this object, as it's rolling, what we just see it is doing is sort of rotating around in a circle. So it's a rotating object. It has some angular frequency, it's angular velocity, we'll call it. Angular velocity omega. If I look at some point on the surface, it has some tangential velocity that's equal to the angular velocity times the radius of the cylinder. Okay. And I know that the period necessary for one complete rotation is given by 2 pi over the angular frequency for the constant motion. And so if you recall where that came from, for constant rotational motion, the angle displacement is given by the angular velocity times time. One complete rotation then, the angle goes through 2 pi, and one complete rotation is called the period. That time is the period of the rotation, and so the period is 2 pi over omega. Okay, so in the time of one rotation, I want to ask, how far has the cylinder rolled? Okay, well, let's go back up here. So in the time for one rotation, that means a spot that was on the top here has made it all the way around. So, at some time later now that it's rolled and that spot is now over here. This is the center. And see, so sometime later that's rolled, this spot has made it to the bottom. Sometime later now it's rolling back around. The spot has made it up back over here, say, and then sometime later the spot's made it all the way back to the top. If I sort of track this spot out during time, over time, I see it make, some sort of path that looks like this. But this is now the distance that this object has rolled during one period. This is the time. Because once the spot on the top has made it all the way back to the top, this object has rotated 2 pi degrees, and so that's the definition of one period. Okay, so how far did it go? So it started here, and it ended here. So how far is that? Well, if you think about it, this length is the circumference of the cylinder. So it started here. Here's a point at the bottom, and by the time it rolled all the way to the end, you have this point on the bottom has come back, and so you've mapped all the length of space that it has rolled on to the length of surface around the cylinder. And so you can think of, let's say this were covered with orange paint, and as it rolled, it took off a very thin layer of paint as it rolled all the way along. It would take off one layer of paint over the entire cylinder to go this far, and so this length then is equal to the circumference of the cylinder. So the circumference of the cylinder is 2 pi times the radius of the cylinder, which is r. So what is the velocity then of the center of mass of this object? I'm not looking for the tangential velocity. I'm now looking for the velocity of the center of mass. Center of mass of this object. Well, the velocity of the center of mass then is equal to the distance covered divided by the time. We say we're constant rotation. The distance covered divided by the time it took to cover that distance. Well, the distance covered was 2 pi times the radius, and the time we already determined was 1 period. Well, 2 pi over the period, that's the angular frequency, angular velocity, so this is equal to omega r, which is equal to the tangential velocity of an edge of a point at the edge of the cylinder. This is the magic relationship. The center of mass velocity is equal to the tangential velocity of a point on the cylinder. The velocity of the center of mass of the cylinder is equal to the tangential velocity of a point on the cylinder. And so remember, this is the two conditions is that it's not slipping and it's on a flat surface. Okay, but this is the important relationship that we want to use. And now if at any instant in time the system is accelerating, we can differentiate both sides, and we get the acceleration of the center of mass is equal to the tangential acceleration, which is equal to alpha times the radius. Remember, this is equal to omega r. Okay, so another way to look at this is if we go back to our cylinder here, or sphere too, any round object that's rotating. And so we have that the object is moving with this, the center of mass is moving with some velocity. Fine. And this is relative to the ground, right? Relative to the ground. So this point, the center of mass, okay, I don't want to say the cylinder anymore. I want to say this point, which is the center of mass point. This is this center of mass point. This point is moving forward with a velocity of the v sub cm, the velocity of the center of mass, measured relative to the ground. Okay, so note that the velocity of this point, this velocity, equals 0 relative to the ground. How do I know that the velocity of this point, the bottommost point, is 0 relative to the ground? That's the definition of rolling without slipping. If this point of the cylinder had a velocity relative to the ground, that is the definition of slipping. So if it's not slipping, that means this point has a velocity of 0 relative to the ground. Well, we know that what is the net velocity? What is the velocity of this relative to the center of mass? That's the tangential velocity. And so we can look at it this way, as the velocity of this point relative to the ground is equal to the velocity of that point relative to the center of mass plus the velocity of the center of mass relative to the ground. Well, this must equal to 0 because the point has to be at rest relative to the ground. So this is saying that the velocity of the point relative to the center of mass is equal to, in magnitude and opposite direction, to the velocity of the center of mass relative to the ground. Well, this thing right here, that's just the tangential velocity. Sorry. the tangential velocity then is equal to negative velocity of the center of mass. There's the tangential velocity of that point of this object rotating here in a clockwise direction. Now, I mean, so this is vectors, right? So this is correct. My velocity of the center of mass is pointing in this direction, and the tangential velocity is going in the other direction. And so so we have to be a little careful, of course. Up here, we were talking about the magnitudes. We didn't care so much about the direction. Here we have the direction determined by the minus sign, but the key element here is that it confirms what we had up before, which is the magnitude of the velocity of the center of mass. The speed of the object is equal to the tangential velocity, the magnitude of the tangential velocity as it's rotating. Okay, one final point on this rolling without slipping is that the same thing occurs if relative to the ground, let's say the Earth's frame, we'll call this the Earth's frame. If the cylinder is at rest and the ground is moving. And what does that mean? Well, another way to say that is if I have a string wrapped around a cylinder, and now the cylinder is at rest relative to the Earth's frame, but rotating, and now I'm pulling a string with velocity v, then I can say the same thing. The linear velocity of this string, which I'm not the center of mass anymore, but the linear velocity of what I'm pulling, and I'll call that, say, just call that v. So that v is also equal to the tangential velocity of the magnitude of a tangential velocity of a point on the cylinder or sphere itself, assuming, of course, that, again, that there's no slipping. And then also, if we differentiate it, we have that the acceleration, if this is the string is being accelerated, that is equal to the tangential acceleration, which is equal to the angular acceleration times r. And so the idea of this rolling without slipping is the same idea as a string rotating a cylinder or a sphere, where the string is not slipping on the sphere. You have another relationship then between this linear velocity, in this case the linear velocity of the string, with the tangential velocity of a point moving around the cylinder.